The example that we actually used was something very simple, where we have a service that takes a long time. So in this example, it's producing some JSON that is using a value that takes a long time to compute. You know, in microservice type environment, there could be a big fan out of services, and it could take a long time to actually get the final result for compute value to return. So in the example that we actually used, we have this service taking a full 100 milliseconds to complete. This is the type of example that motivates the development of asynchronous APIs. I don't know how many asynchronous HTTP APIs are out there. There's asynchronous serverless APIs and so on. So we just wanted to see what it would be like without just using synchronous. This is basic. Everything is synchronous here. The thread will be tied up. Jetty's thread will be tied up here for the duration of this service. So let's look at the horrible slide that we get when we actually run and we throw a load generator at it. So this is a graph using a load generator that's generating a load of about 5,000 HTTP requests per second. The way to look at this graph is on the x-axis is time. So this is a 30-second duration run. The y-axis is the latency, and it is horrible. So we're using here the default configuration of 200 threads. If each one of those is tied up for 100 milliseconds, this server is not going to be able to handle more than 2,000 requests per second. Yet I'm throwing a load generator at it that's generating 5,000 requests per second. So the latency here is really, really horrible. And what's worse is the number of HTTP requests that are being dropped. I'm actually seeing about 45% of their HTTP requests are being dropped in this example. If I were the admin of the server, I'd say, I'll just add more threads and fix this problem. And I do that, and I get a slightly better picture. I've doubled the number of threads, so the max latency has actually decreased, but I'm still getting a lot of drops here. In this example, which was actually on a 12-core system, I think it was, and we were still getting about 15% of the HTTP requests were actually being dropped. We replace this completely, no thread pool, we just use fibers for every single HTTP request, and this is what we actually get. It's a very, very different picture. Now, it's a bit slow at the beginning, and we know exactly why that is in this example. But the interesting thing is there's no drops. I can actually double or treble the load here, and the latency will mostly stay constant because the server is not over provisioned. And the reason this works, of course, is because somewhere in that compute value, we're actually doing some blocking operation, whether it be a locking operation, I/O operation, but it's causing the fiber to actually park and freeing up the thread to be useful for something else. So this, we think, is a very compelling example if we were to get fibers to be able to run most existing code. Now, our current prototype, we have a couple of limitations.